some of the things that we've already come up with, and we're going to see how this manifests on this vector model. Okay, so recall the particle on a ring. Energy solutions were Jz squared over 2I, which is also equal to ml squared h bar squared over 2I, and thus my quantized angular momentum is mlh bar. And specifically, I know it's a J sometimes and an L sometimes, but capital JZ is specific to the angular momentum on this Z dimension for a particle rotating on a ring. Okay, we get mlh bar values. So when we did particle on a sphere, all right, we got that the energy solution is L times L plus 1 times h bar squared over 2 times I. All right? And so what we are seeing here, what's pretty cool, is now we have ways of connecting the projected Z length and the total magnitude. Okay, so if you look at how these two equations connect now, what we can now say is our total magnitude, which is going to be this LZ squared, all right, is going to be equal to our JZ squared result, which is L times L plus 1. What did I do here? I'm going to erase all of this. I'm going to start over. So basically what ends up happening, right, is that we get JZ here equals mlh bar for this particle on a ring for the two-dimensional model, and expanding that out into 3 dimensions, the total magnitude becomes L times L plus 1 square root h bar. Okay? So that comes from substituting the fact that we've got this mlh bar, ml squared h bar squared, and L times L plus 1 h bar squared. Okay? So here we're going to see this mlh bar is our projected Z length, and this L times L plus 1 h bar is our total magnitude. Okay? So I'll remind you also that angular quantum number L takes on values 0, 1, 2, etc. Our magnetic quantum number takes on L dependencies, so ml equals L, L minus 1, etc. Okay? And then from this ml, we get this 2L plus 1 values of ml. So how do I get 2L plus 1? So let's go through this. So if L is equal to 0, ml has to be equal to 0, meaning JZ has to be equal to 0. And if L is equal to 0, 2 times 0 plus 1 is just 1. So there's only one degenerate state for ml equals 0. So that's what this JZ2L plus 1 degeneracy is. What if L is equal to 1? Well, then we know ml is -1, 0, +1. And so that means JZ can take on values of 0 or plus or minus h bar. Okay? And so the number of degenerate JZ states is 3. And we get 3 because if L is 1, 2 times 1 plus 1 is 3. Okay? And then so on. If we have L is equal to 2, then ML can be -2, -1, 0, +1, -1, -2. We can see the values, the permitted values of JZ, and then of course the number of degenerate states. Okay? If you're seeing connections to the periodic table here, then you've got a really good eye, because that's what's coming. Okay, so now, how do we connect these two things? I'm going to draw an arrow and a question mark. How are these two ideas connected? All right, so I think this is where this gets really cool. Okay, so if, and I wrote here JZ squared, but really that's LZ operator squared, because it's the total magnitude. All right. So if the Z component, the projected Z length, is mlh bar, and here let's make a coordinate system. Okay. So I'm going to draw that right here with my origin starting at this triangle, where now this is, let's call it X, Y, and Z. Okay? So now we can see my z component of the vector is given by ml h bar. And what's important to note is I know this value. We know this. So because if we know the quantum number ml, then we know what the projected length is, right? If ml equals 1, then we know that this length, the length of this vector, is h bar. If ml is equal to 2, then we know that this is 2 h bar. Okay? So then what about this? Well, my projected magnitude is given by root L times L plus 1 h bar. Okay? And I can turn that magnitude into projected length by taking the square root. And so now I get that the length of this vector becomes root L times L plus 1 h bar. And this makes a 90-degree triangle. And the reason why it makes a 90-degree triangle is because we know this length and we know this length. And remember that my particle is going all the way around full circle. Okay? So that means this length has to be fixed and given by the angle theta. How do we get that angle theta? Well, SOHCAHTOA, right? Remember, cosine is the adjacent over the hypotenuse. And based on the way that I've drawn this picture, we can see the cosine of theta is then going to be the adjacent, which is ml h bar, or just ml at this case, over the hypotenuse. So what this means now, all right, we can specify the projected length. We can specify the z component of the vector, that with no uncertainty situation whatsoever. And now what we get out of this theta is we learn what that angle is. So in other words, back to my same z, y, x coordinate scheme, I'm going to use a different color. What that means now is the way my particle is rotating, right? In the two-dimensional model, it was just going straight up. But you can see, right, this is given by my projected length. So this is accurate by calling this jz, my projected length here. Okay? So that means this particle has to be pitched out by angle theta, which it means it's going to be rotating around like this. Okay? Very cool. And so now what we see is by having different values of ml, we have different z lengths. And if the jz value is fixed because they're all degenerate for a given value of L, that then predicts as the ml value is changed, we get different angles of rotation. Okay? So let's, or really I should say different angles of our orbit. So here's what that looks like. So suppose L is equal to 2. So then we know that we can have ml equal to +2, +1, 0, -2, and -1. Are all of those states degenerate? Well, let's think about it. So if L is equal to 2, right, then we know that that projected, or then we know that, excuse me, the angular momentum is given by the square root of 2 times 2 plus 1 times h bar. 2 plus 1 is 3 times 2 is 6. So in other words, all of these jz lengths will be root 6 h bar. Okay, so let's look at this picture right here. ml plus 2, the length of this arrow is root 6 h bar. ml equals 1, the length of this arrow is still root 6 h bar, and etc. So I'll keep writing those in. They're all length root 6 h bar based on my, I don't know why I wrote root 6, root 6. So root 6 h bar. Okay, so that makes them all degenerate because they all have the same angular momentum. So in other words, because they all have the same angular momentum, that means they have the same frequency of rotation, right? They're all rotating the same. And so the only thing that changes now is as ML changes, it's just changing the way that this pitches out in that other dimension. So for example, when ML is plus 2, we know now that this length is 2 h bar, okay? When ML, and so I'll draw that right here. When ML equals 1, we know that this length is just h bar, and because that adjacent length has shrunk, that means my angle theta has to increase by SOHCAHTOA, right? And so that's describing that extra pitch from the ML plus 2 state to the ML plus 1 state. Very cool. And so what you can also see, ML equals 0, there's no angle whatsoever because ML equals 0, there's 0 z component. So this describes a particle that's rotating perfectly in the z plane. We're going to see that this ML equals 0 is a special case as we start building up our description of the atomic orbitals. And we'll see that ML equals 0 is specific to the z-axis. I know that we don't have angular momentum in the z-axis, right? Our angular momentum is pointing out that way, but our rotation is occurring in the z-axis, okay? So now I just drew the ML equals 0 state again, just so now we can compare that to the ML minus 1 state, right? So now this length is minus h bar, so it's still h bar, but it's just now in the other direction. And of course, now this length is minus 2 h bar. And so now I'll also remind you, our particle is spinning round and round, right? And if you recall, when we did our square modulus of psi ml, that result was 1 over root 2 pi. So that means no phi dependence. Okay, so when we look at this picture over here, so remember, out this way is theta, and this way is phi. So the fact that our wave function has no phi dependence means it's spread out over all angles of phi. So what we get from this space quantization are these projected cones, okay? So these projected cones represent our angular momentum, right? So you can see here is that plus 2 state, okay? And we can see the particle is spinning round and round and round, but because we know that there's no phi dependence, then that, right, that root 6 h bar at angle theta, okay, it smears around all phi angles, okay? So this is what we call, this is the space quantization model, all right? So it's important to note that this is not psi squared. This is not where like we expect the particle to be. It really just kind of represents the fact that we still do have a Heisenberg uncertainty situation going on, okay? And that Heisenberg uncertainty situation is Jz and phi, right? So we can specify this length here, but because we don't know where the particle is on this angle phi, that's what predicts this spreading all the way around. So we still have uncertainty in our angular momentum, but we've narrowed it down to these conical areas. Okay, continuing.